There is one very common way that we can see forces between charged objects. You can see it in the picture of the boy below. You might also experience it when you take clothes out of a dryer, as we talked earlier. So why do you see it in the boy here? Well, all his hair strands are repelling each other, so they almost have the same charge on them somehow. And that actually came as he was sliding down this plastic slide here. So the below simulation will help you answer this question, so please click on this and watch it. If you performed the activity on the previous slide and didn't just watch it, because frankly nothing would have happened unless you perform the activity, you had a balloon in a sweater. What happened when you rubbed the balloon on the sweater and then let it go? And we're trying to give you a hint over here. Please go to the next slide for the answer. The balloon was attracted to the sweater, so charges were exchanged between them, so they were now oppositely charged. So this is telling us that forces are exerted between charges. These forces are called electric forces or electrostatic forces if the charges do not keep moving. Like charges, positive and positive, or negative and negative, will repel, and unlike charges attract each other. So what we're showing here, we have two positive charges, and then the arrows show the direction of the force on them and which way they're going to start moving. So we've got the positives repelling, the negatives also repelling, and then the positive and the negative attract each other. The electrostatic force is not a contact force. Contact forces would be where you're actually touching something, like pushing a wheelbarrow, or pushing down on the ground, or pulling a rope. This force acts over some distance of separation. Like the hair strands on this kid here, they're all pushing each other away, but they're not touching each other. So that is not a contact force. And again, unlike charges repel, like charges repel, and unlike charges attract. So here's a video on fun with static electricity. There are two main factors which affect the size of the electrostatic force. One, the size of the charge on each object, and two, the distance between the two objects. As the amount of charge on either object increases, the magnitude or strength of the force increases. And here's a key point, that's why we've got it in bold. The force is the same on each charge regardless of each charge's magnitude. So if one of the charges is doubled, the force doubles. And what we're trying to show with this picture, we have two charges here. Let's say each one is +1. The red arrows show the forces on each one, and they're repelling each other, they're moving away. And you can see that the forces are the same. And you'd say, okay, they're the same charge, not a big deal. Then we replace this +1 with a +2. The charge now gets larger, it actually doubles. But notice the length of this force vector and this force vector. It's exactly the same. So the same force is acting on each of the charges, even if they're different. Now, let's double both charges. What happens to the force? Well, now the magnitude of the force is multiplied by 4. It is directly proportional to the product of both charges' magnitudes. If the charges are moved farther apart, the force will decrease. So here we have a case where the charges are initially a distance d apart, and we move them to a distance 2d apart. The force will decrease by a factor of 4. The force is inversely proportional to the square of the distance. So you double the distance, the force decreases by a factor of 4. The force between the charges decreases as the charges move apart. So we have a quick graph over here where we have the distance between the charges and the magnitude of the electric force. Notice it's not a straight line. The force falls off very quickly with distance. And it's not proportional to the distance, but it is related to 1 over the square of the distance. So if we were to triple the distance, for example, the new force would be 1 over 3 squared, or 1/9. Let's put both effects together on one slide. the electric force between two charges is directly proportional to the amount of each charge, and the force is the same on each one. The force also decreases in strength as the charges move farther apart, and we'll give one more example. Let's say they're now 4 times as far. The strength will go down as 1 over 4 squared, or 16, so 1/16.